Hello. Yeah. All right. Yeah. Thank you for the introduction. And yes, I'm excited to be here. Yeah, very nice talk just now. And I think I can pick up from there a bit. I am going to talk a bit about uh, latent world models, which is world models are a very overloaded and hyped word right now. So I try to break that down. And also a bit about our new lab. We just started this non-profit research lab called Kesai. So we are in Tübingen in Germany and also have an office in Paris. And basically, what we are trying to do is build really efficient driving policies first, but physical AI policies down the line. Um, Emphasizing that we want things to be fully open and reproducible. So actually, like I gave a talk on Monday, which is also recorded in one of the ICRA workshops, where I focused more on like the open source strategy and why we think that's really important. But today is going to be more about what can be done to make things efficient enough that we can build high performance policies that are fully open source. All right. And to get started, before we go to word models, I think we need like a quick primer on VLAs. You've probably heard a lot about VLAs at ICRA. I wanted to just define it in a similar context to word models for later, which is that VLAs are trained to predict expert action. So these are imitation learning models at the core. They're trained on large sets of human demonstrations of doing a task. And the most interesting thing is like, given the world state, they predict the actions after doing an intermediate reasoning trace prediction in natural language. And like I almost see this as the evolution of the perceive, predict, plan sort of modular approaches of the past. You predict the world in a very flexible language format before giving the action output. So in this case, this is a model called AlphaMayo. It's from NVIDIA, from my former team actually. And the reasoning before the action is something like the vehicle is going to wait until the traffic light turns green. So it's generally like a prediction of something that a key agent in the scene is doing that is relevant to the behavior your agent needs to perform. And yeah, there's many advantages of these models, particularly in handling rare cases because the text format is so flexible. It can deal with predictions about really rare objects well, even with few examples of such objects. Um, and you don't need 3D or 2D, or you don't need human, like very specifically defined labeling pipelines to generate the labeling that you need to build these sort of models. So you can just take a frontier like GPT 5.5 or whatever and ask it to generate relevant text data, have it like manually curated a bit by some humans, and this is your labels for this kind of prediction. Um, and so, like, this has pushed sort of the performance and deployment of autonomous vehicles a lot, but there are like obvious flaws with VLAs still. If you do a classical prediction to plan, you can kind of be sure that your planner is not going to collide into a vehicle that you predicted is moving a certain way. But with the VLA, it has this ambiguous text prediction and a action output which is not necessarily enforced to be aligned. So it can have a, like we also know this from LLMs, like the reasoning is not the true causal reasoning behind their actions. It's just a scaffold. And this is kind of problematic, and why these models need a lot of data. Um, it's also like because these models are so dependent on the web pre-training, the vision and language modalities are kind of the focus, and incorporating like other data like radar, lidar, touch, like other kind of sensing into VLAs is hard. Often you run VLAs with a redundant background stack. So you have the end-to-end VLA, which is mainly doing vision with a couple of cameras, and a LiDAR-based background like classical stack, which is arbitrated, again, using this language in between. Like, I think the biggest flaw, though, is like these models are just so huge. They're like 2B, 10B parameters. with most of these parameters dedicated to random fact memorization, which is not really relevant for physical AI tasks. So you have a lot of these advantages from the beginning, but in exchange, you are dealing with a lot of difficulties due to like things these models were not defined for. So a bit more on the inefficiency. So um, this particular model, the Alpamayo VLA for driving, is trained on 80,000 hours of data, which is a lot. Like this is 80,000 hours after curation. Like it could easily be like over a million hours before that. And that is like 1,000 hours from a fleet of 1,000 cars. So this like really limits the number of like organizations that can actually build this kind of model to ones that have very large fleets. Also on the compute side, this model like has this very long pipeline it needs to go through. Even assuming you just grab an off-the-shelf pre-trained model, which gives a lot of initial capabilities, just the task specific. So in this case, driving specific training is another 60,000 GPUs. So this is again like 500 GPUs for a week or so, again beyond the reach of most organizations. And you have many further stages like RL, and here both for the RL and for the deployment, you need this model to run fast on the hardware. But this is also hard because of their large parameter counts. And so this brings me sort of to like what I think is a promising direction in the near to midterm is looking at world models. They come in many flavors, but I'm going to talk mainly about two of them today. One is this emerging line of things called video action models, and the other, which I get to later, is called action video models. And I will, detail what these mean in a bit. So let's start with the video action models. So I defined it in a way very similar to VLAs. These are also imitation models. They predict expert actions. Um, Also conditioned on world states. The difference is the reasoning state traces in VLAs are text. So you output like this textual description of how the scene is going to evolve. Whereas like video action models actually predict in a more classical sense. They predict the direct motion of the scene in the state representation. And specifically like what I talk about today is work that's going to be presented at CVPR this weekend again. Which is a latent video action model. So the idea is that this is an example. You have a scene, the VLA would predict something that looks like this. This is a cherry picked example where it hallucinates and the output is wrong. So it drives into another vehicle essentially because the text kind of hallucinates that there's no other vehicles and so on. And the idea is like, can we build a different kind of reasoning that is object aware and spatially aware. And doing so, we're going to achieve two things. Like, first of all, like it could be better suited to reasoning in spatially, like tasks involving spatial precision. And secondly, it's going to be more efficient. So text is like just a very verbose and like non-compact version of like describing things like in driving. So if you already have the reasoning in a space relevant to the task, you can do it with much fewer tokens, is the idea. So how do we do this? Actually, like this model is like quite similar to VLAs, but scaled down a lot. So we have this, what I call the latent video action model here, which is initialized from a small LLM. So it's a QN.5B LLM backbone, and a video input coming from the like front camera of the vehicle is fed into this through like a dyno encoder. This is like pretty standard for VLMs. You get some proprioception input, and now you want to create this reasoning trace, this latent reasoning trace. Here I kind of go over ideally what we wanted to do, and the next slide I'm going to talk about how we achieve that. But the idea with this reasoning trace is that the model predicts some sort of latent representation of the scene state. So some encoding of these objects and the map and how they're moving and so on. And we do this by basically building a tokenizer of this abstract scene. So this is like kind of an autoencoder which says like, this is a vector continuous embedding of this scene state. And have the model predict, first of all, from the images, the initial scene states embedding, and then from these embeddings, a tokenized action. And this is done in a chain. So the idea is we want this model, which was pre-trained to predict text tokens. So it was just a VLM, to now predict these new kind of tokens, which are interleaved state and action tokens of your specific task, which you build specific autoencoders for. And not only do we want like one possible rollout of the scene, we want to let it do this multiple times. So we also have this superscript here on the actions and states, the I, which says you can allow this model to now explore multiple possible action sequences and predict its expectation of how the states are changing in response to these action sequences. And once you're done with this, you end the reasoning and predict a bunch of action tokens in, again, the same tokenization space as these actions. This is very convenient because it lets you see how aligned these final output actions are with the intermediate reasoning ones, and lets the model do different strategies. It could, for example, use the chain of thought for coarse to fine prediction, like start off with something and make it better and better. And by that, you would see the alignment improves over time to the final actions. It could do branches and elimination. So it could like try like 3 different things and then say, this was the first one was the best, let me go with that. Or combinations thereof. Like it could like just do a bunch of bad examples, reject them all, and predict something completely new in the end. So it actually has the flexibility to try all of these strategies. And yeah, there's a lightweight decoder to get this out. So the surprising thing we found is that with much smaller models and only public data sets, we get quite interesting results with this kind of chain of thought. And this has to do with sort of the balance of different training stages. So there's 3 main stages in training VLAs or this kind of model. The first one is the pre-training for driving. So you have the VLA, which is already trained on general internet data and maybe also robotics physical air data. But you need to do a lot of driving specific training to first make it domain specialist. So for this stage, we found that like we could use a much smaller model and use much smaller data set. So the Alpamayo VLA, for example, is trained on 80,000 hours of data, as I mentioned. This one is trained on only 2,000 hours of public data. So it's like much less data, and because of the smaller model and data set, much less compute. But then the interesting thing comes next. So in the VLAs, you would typically need to learn the reasoning in this supervised fine-tuning stage. So in the first stage, there's no reasoning. I forgot to mention that. You just train the encoder and the trajectory decoder. The second stage, you kind of build this reasoning chain and you do it with rollouts from the base model. So the base model, which you just trained in stage 0, proposes actions. The state embeddings for these different actions that are proposed, you just encode the real ground truth state. And this actually just creates a template of what you could use for reasoning, because like you're just taking random actions and seeing how the scene evolves and training the model to predict this at this step. Whereas in the VLA, actually most of the reasoning is learned in the stage 1. In the VLA, like you're giving the model the actual reasoning that you expect it to output during the stage. So now when you get to the final stage, this is where actually the bulk of the learning happens for our setup, because like so far you've only learned the scaffold of like, this is a template for how scenes could evolve given an initial state and actions. You can now do reinforcement learning where the model can discover these different strategies of potentially doing the branching or potentially doing the coarse to fine reasoning. So you only supervise on the final trajectory output, but because the model has this like intermediate set of tokens that it can use flexibly for different things, it can learn these different ways of using them for different tasks. And what we've done basically is, compared to VLAs, we have shifted the compute burden from the pre-training to now we do more learning in the reinforcement learning, the post-training, which means we can do it with less data. So in the end, we're getting more out of the limited data we have because we're allowing the model to explore more reasoning strategies given the same data. And this like project, it was done at NVIDIA, but still on very like resources within academic reach. So it's like one node for a week the training takes, including all of the stages. Roughly half of it in the final post training stage. Yes. So okay, we have now a way to train a very efficient model, but what about its performance? It's very hard to measure performance in driving. Like a lot of my work during my PhD and also before was on benchmarking, but yeah, on some tests where like we do a test in this paper on 30% of regular driving and 70% of specific hard cases, we find similar performance to a VLA of like similar performance to a VLA of similar size. So these are collision and off-road rates, the typical metrics. And this is like an open loop evaluation. So this is not like best practices, but for these large models, this is like quite standard for how you evaluate them. And as you can see, each stage of training that I mentioned makes a big difference. And in particular, the last RL stage, since lower is better, you kind of half the collision rate, and that's when you become competitive to the VLA once you do this RL post training. And independently, like just yesterday, there was this paper called Omni Dreams that came out, which does this at a larger scale and comes with similar results in a more like expensive and principled evaluation setting. So the VLA policy, which is on top, which is trained with 4 times more data and 5 times more parameters than this one, which is a video action model, has higher collision rates and similar off-road rates. So I think like the main takeaway from sort of this half of my presentation is that you can get more out of your pre-training by really thinking about the reasoning you use, and VLAs are useful. So again, these results are biased by the type of test set you evaluate in. Obviously, if you have like really out of distribution rare objects which are not even represented in your bounding box space, the VLA reasoning is going to be better there. But if you have tasks involving very precise maneuvering, the spatial reasoning is going to be much more useful. And by thinking carefully about like how to incorporate the right kind of reasoning, we can probably get a big boost in data and compute efficiency compared to just blindly going into VLAs and scaling up the data as currently is being done. All right. And so now let's talk a bit about the other kind of world model, which is the action video models. These are like the exact inverse of the model which I just showed you. So the important thing here is that you're now predicting the world states. That's the main task. And you are conditioned on actions which are not necessarily expert actions. So in video action models, you are essentially doing imitation. So you're training on demonstration data of good driving. Whereas for these sort of models, you should also be able to predict what happens under bad driving actions. So you're training on both or like the full possible action distribution. And given the world state here, like illustrated as a video and an action or like an action sequence, you need to predict the imagined future world state. Typically, this is done in state space in these models, and importantly, some kind of task relevant reward. So, the end goal of these models is typically either simulation or deployment. So, if you have a simulator, you want to train some model in it later, you need this reward to tell you, like, of all the actions it took, which ones were useful. And we've been building these kind of action video models like already for a couple of years. This is work from around the end of my PhD, where already like in 2024 you could get visually very nice looking video predictions from these models at high resolution, at high frame rates. But it took a long time for these to become useful for deployment. And that's what I'm going to talk about today is like, how can we actually take these kinds of models and generate value from them for actually deploying autonomous vehicles or robotics policies? And I think the two key blockers that were preventing these from being super useful were firstly, the reward prediction was really hard. So there wasn't like a super nice way to get reliable rewards from these videos that were predicted. And secondly, these models were just extremely slow to infer. Like you would need to use like multiple GPUs for multiple minutes to generate a few seconds of video clips, which made them really impractical to do things with. So what changed? I think like the way that we've managed to get some interesting results out of these is actually like we've modularized a bit. So we use 3D Gaussian splatting, and this is like a work called World Engine, which is very soon to be on archive. We use 3D Gaussian splatting as an interface again, like to this latent space. So we don't directly do these diffusion models and this prediction in sensor space, but we do it in a abstract representation. In this case, like the maps and bounding boxes. And we use 3DGS or like this offline 3D or 4D Gaussian splatting as an interface to take your large data set, curate sort of the most interesting part. And again, the theme here is to like increase the value of your most useful data. So here we took like around 200,000 clips from this was a collaboration with Open Drive Lab in Hong Kong and Huawei in China. And like we have a large data set, but a subset, around 2% of it, is reconstructed with 3DGS. So that you have these abstract representations. You can build this abstract future prediction model, and you have an interface from the abstract future prediction to get back sensor data, because that's what the 3DGS gives you. And then on top, some rewards are very easy to predict in such an abstract representation. So things like time to collision or drivable area compliance, which are useful rewards to help your model become stronger, are hard to predict directly on pixels, but much easier to predict in these abstract spaces. And so now we have this setup, and what we did is like we took also the large data set. It's also again 80,000 R, so similar in scale to the Alpamaya one I mentioned in the beginning. And we pre-trained a policy which is much smaller. So this one is around like 5 to 10x less size and less compute than what you needed for the large VLA, but managed to post-train it to get a huge amount of performance improvement through reinforcement learning in these generated worlds from this action video model. So the typical pipeline is like the imitation pre-trained model proposes actions. They are like in this latent representation rolled out, and it can try different actions, gets different rewards, and you use GRPO or typical NERL loss to supervise it to do things that got higher rewards. And we show that this post training is really like, so we have one experiment in simulation where we control things, and we show that the data which you can bring into this post training loop is 14 times more valuable than data collected just off policy, just data collected by a demonstrator. Because in the interactive data, your policy can try things out, it can discover like exactly how to recover from the kinds of failures it makes. And this sort of like lets you keep scaling with limited amount of data to higher performance, which gets very hard from only passive collection. So this is sort of the like the takeaway here is that the action video models can kind of generate value by making your static data into interactive data. So even if you have limited amounts of it, you can get more value out of it. So we took this policy and we deployed it without any backup stack. So this is just an end-to-end model trained on just this data with only the approach I showed you, deployed in Shanghai on these Huawei vehicles. They have a dev mode. You can just let it run, and it drove for over 200 kilometers without any interventions. This is a scene where like you can see sort of the things that emerge from the sort of end-to-end data-driven training and the post-training. So here, for example, there is a construction zone and it needs to drive in the opposing lane before merging into the normal lane, and does this quite seamlessly. Here there is a occluded or like hard to see pedestrian coming out from the side. Also handled super easily, and like even in just our single like field test, which was like not very extensive, you see super hard out of distribution situations, which would have been very difficult to tackle with the 5 year ago, 10 year ago approach to driving of these like modules. So here you have an excavator, it's night, it's raining, you need to, inside an intersection, go into the opposing lane and go around it before the light turns red. So all of this was done sort of, it's not zero shot like this city. This is from Shanghai, and like Shanghai is in the training data for this model, but still like very impressive nonetheless. I think that you can do this, and we fully know the pipeline towards achieving this. So like the all the details of how we got this result is now open. Um, but yeah, this brings me to the last point, which is like everything I've shown you today is kind of partially open. The Alpamayo, they open source a very large foundation model that you can do some data curation and some like data pipeline tasks with. The LC drive, the data set is open. Like I mentioned, we did it with like that was this the video action model. This one, yeah, you can probably reproduce it, and but the model is not. And then now the Huawei work, the world engine, which I just showed you, also like most of the code and tooling is open, but the data is not open. So you always have this problem in the driving space that because so much resources go into building these policies, both in terms of data and compute, it's very hard to make them fully open as a reference. And this is actually happening in other communities. So like there are like for example nonprofits in LLMs like Alan AI. They release these Olmo models where they release everything. They release the data, the training recipe, the models, and you can fully do it with medium scale resources. You can get it out. And so this is sort of the goal of like our new nonprofit organization. Can we do this for physical AI and for autonomous driving to start? And I think for this, like we can go with a reproduction of what is currently available, but probably we need like another order of data and compute efficiency before, with just public resources, we can make competitive and useful frontier policies. So like I think there's like a lot more research to be done, and I quickly close with some ideas on that. So um, this is the data set I've been mentioning, which was used in like LC drive. This is the 2000 hours of public data from NVIDIA that is allowed for commercial use. It's like fully open. And what we've done is like we have taken this data as a core and created a library called 123D, where we combine this with all the other public autonomous driving data released till date. And this really does get you some scale. So we start with the 2000 with all of this together, gets to like 3000, 4000, and we're talking to various organizations, partners to open source more and more data into this collection and make it super easy to use. So do check this out if you're working on driving. But I think even this is like much smaller than the works I just showed you. Another interesting development is like there is recently like organizations putting out lots of synthetic data. NVIDIA, like this one was announced like I think 2-3 days ago, put out 2000 hours of edge cases that are created with LLMs and with some scenario mining, looking at real world failures and getting like interesting events and using these Cosmos models to make them look more realistic. But then like putting this all together, this is still all offline data. It's kind of like what I mentioned in the world engine part of the talk. You need to be able to make this interactive. So at the same time these data sets are coming out, we're getting simulation tools also coming out. So we have this Omni Dreams and Nurek and also the world engine, which I just mentioned. They are simulators in which you can do this sort of like on policy exploration. You can collect data exactly of what your policy fails at. So these simulators get inputs that look like one of these. So either the 3D world projected into the image plane or in bird's eye view. And they come in different flavors. So you have like 3D GS based ones like Nurek. Nurek is like, it does 3D Gaussian splatting and then uses a diffusion model on top. You can see the person has like legs missing or something. It's like it has like slightly different failure modes. It's better at some things worse than others. Omni Dreams is like a full action video model. It's like kind of like one of the earlier first works I mentioned. So it just like uses a big diffusion model to translate this input directly into these pixels. Also trained on a lot of data. It's a bit slower. Um, the point is like you have like these various sources of data now. We have like real data, the offline synthetic data, stuff like world engine, which is like 3DGS simulation, combination of 3DGS and diffusion, and then fully diffusion simulators. You can get fairly large data, but it's all very complementary. The real data is more realistic. but has like less interactivity. Whereas the simulation data has like many visual flaws, but is interactive, and you have like you need some kind of infrastructure mechanism, I think, to bring these complementary benefits together. And I think this is where like there is still further things that can be done with world models. And latent world models, I think, are a great candidate for this. So you can design a world model which is like very similar to what I showed in the world engine, but using two new things. One is you learn the encoder. You don't have a static abstract state of like bounding boxes and only diffuse that, but you can learn an encoder end to end in this world model setup um, by training it on all these sorts of data. So because these models are not restricted to expert data only, you can train them on data from random policies in simulation together with all your real data you've collected. And it basically enables you to then input real data and simulate it as you would with a simulator. This is like the idea behind like Dreamer or like some of these like model based RL line of works. And because you have all these things like motion tracking or like the language, which I mentioned in the first part of the talk, that you can like think about your reasoning and learn good representations. I think these sort of latent world models will start looking a lot like this, where you use different kinds of extracted signals like motion tracks or like these text descriptions of how the scene evolves as the state you're predicting the future of. And this helps you learn also a strong encoder because you're predicting task relevant things, and builds this sort of data and compute efficiency you need, which you don't get from just predicting pixels. Um, all right, so this is my last slide. I think like the final sort of takeaways are we are really pushing the efficiency frontier. I think like we are getting closer and closer to the point where in open source we can have like really strong driving and robotics policies. The video action models help representation learning because like learning to predict these states is like a very strong supervision signal. The action video models make your data more interactive and like help you get more out of limited data. And I think like latent world models can help us kind of jointly both learn strong representations and simulate, make your static data interactive, which is going to be one of the key factors among many others to making these sort of policies like very efficient and open. All right, so that's it. Thanks for your attention. And yes, if you're interested in this research or interested in doing open source, we are hiring. So you can find us at the link up there. Yeah, thank you.
Thank you, Kashyap. Thank you for the talk. We have time for a couple questions. Yes, please. Yeah, if you come here, that's easier.
Thank you, Kashyap. Great talk. I have a question which I think you partially answered in your second to last slide. So in your reasoning that you proposed in the first half of the talk, you're reasoning in this very limited latent space. If you know Rohan, probably you know his favorite example of a stop sign on a billboard, where you need reasoning and reasoning in language space in order to pick the right action, right?
Yeah.
Which I assume these limited latent spaces are removing this ability of reasoning in a higher dimensional space. Do you think that this other form of encoder, which I didn't fully understand, could enable this reasoning?
Yeah, so essentially this, I think, so first of all, like I think like the reason that we get away with strong policies, even though we have this very limiting representation in between, is because the policies are still end to end. So if you see enough data, you will still make that connection without the explicit reasoning. So that probably won't work for these super weird stop signs on billboards. But I think in some cases you will always have that like non-reasoning connection, or it can reuse this reasoning in weird ways. So this we see happening even if you have a limiting representation. Like sometimes like these models do weird things, like they create these registers where they just put stuff which is not what you intended. So I think that is happening to an extent, but I do think in the longer term we do need this like multiple forms of reasoning. And like here the encoder, like how I think this might address that is that I just think like we use multiple encoders. Like we use a language encoder for encoding the language auto labels you have regarding the scene. Also use, I don't know, like depth anything, like a stereo based depth model, a tracking model for generating those specific signals, and ask the diffusion model to kind of denoise these signals given the past video. And the idea is then the encoder will need to learn if this is also trained. Like, so again, there's like very initial sort of abstract ideas, but if the signal is somewhere in the input, you have the infrastructure to learn from it, is the idea.
Okay.